Okay, we've been peeling back the hood or visiting the sausage factory for how these random variables get generated. And we've looked at the inverse transform method, which is kind of the basis for a lot of them. We've seen the composition method, and then you started talking about the acceptance rejection method. So I'm going to give some more examples of that because it gets a little involved and you kind of have to keep your finger on your place when you're doing that. So with that in mind, and I'm exploring this just specific examples of this beta distribution. The beta distribution is one of my favorite distributions because it's very flexible in terms of its shape. Other random variables like like exponential or like normal, the normal, regardless of how you the normal, you can kind of shift the mean, you can kind of scale it using the standard deviation, but it's always going to look like a bell-shaped curve. Whereas the beta distribution has just a variety of different shapes depending on the parameters you give it. And it's a nice way to illustrate this acceptance rejection method. So first, we're going to look at the beta distribution with two parameters, alpha 2 and beta 2. So here's the full-blown thing. So the beta distribution in general is it's 1 over the full beta function. There's a thing called the beta function, which is kind of related to the beta distribution. And in general, its PDF is what I'm writing here. And so if we plug in alpha of 2, then this becomes just a normal x. And if we plug in beta, that becomes just a normal 1 minus x. And then it turns out when we evaluate 1 over the beta function, we just wind up with 6. And just as a check, you want to make sure that this whole thing is in fact a PDF. So one way of checking on that is to integrate it. And so in this particular case, we can do that. So if we were to pull this in, it would be like 6x minus 6x squared. And if we integrate that from 0 to 1, then let's see, so that this would be 3x squared minus 2x cubed from 0 to 1. And so the 0 is going to be zeroed out. And then for the 1, we'd have 3 minus 2, which is just 1. So it is indeed a PDF. You always want to make sure that's a check on that. Okay, so now when you have a PDF that has a finite range and a finite domain, as this does here, it has a finite domain. Its domain is 0 to 1. We can shift and scale it as well, but for this, we're just going to deal with the canonical one, which is 0 to 1. And when the range 2 is bounded, then we can use a uniform majorizing function. That's kind of the easiest and most straightforward one, because if you have a uniform majorizing function, then you're just generating from a uniform distribution as your test cases. So remember that, so here's the PDF, what I've been calling sort of T of X. I forgot, just the notation was probably when I learned it. So that's, so the majorizing function in this case is just a straight line, but you have to make sure it's a majorizing function. Now, you can have any majorizing function you want. So I could have chosen a T which is kind of even bigger than that. That would work fine too. You know, any, as long as it's a legitimate majorizing function. If I chose a T down here, that wouldn't work because it doesn't majorize. So that's not a good one. Oops. Right. All right. But the reason, okay, so do you see why in this one, the efficiency has to do with how many of the trial variates you generate get rejected. So in this case, where it just actually is tangent to the PDF, the efficiency is, which is the area under the curve. So if we choose a majorizing function of 3/2, then the efficiency would be 1 over the area. So the base is 1, the height is 3/2. So the area is 3/2, and so the efficiency is 2/3, which is not horrible, but not great. If I choose a majorizing function that's even bigger, then the area under the curve is going to be that much bigger, and so the efficiency is going to be that much less. So if I choose, for example, just to be on the safe side, so if I choose a majorizing function uniform of 2, the efficiency would be 1/2 instead of 2/3. So. Okay, so how do you remember that? Keep your finger on the place. The majorizing function is not a PDF. It's almost a PDF. It's a PDF when you divide by the area. But the important thing really is just kind of the shape. So the shape of this is a uniform distribution, and so we generate from that uniform distribution as our test, but the key ratio is the original density to that majorizing function itself, not to the majorizing PDF. Those are two different things. And so just kind of plugging in, our majorizing function is 3/2, our density is 6x 1 minus x. So when we do all that, we get 4x 1 minus x. So our method is, we're going to, and kind of what you call it sometimes. So we're going to generate a U with, well, here's our test. The Y is going to be from the uniform distribution. And what you call it doesn't matter as long as you're consistent. So the Y is going to be from this distribution. And then the U is going to be testing whether we accept or we reject. And the way that it works is, well, we accept if that uniform is less than this ratio when our test random variable is plugged in. And so what we really would want here is a repeat until. So if we had a repeat until, it would be repeat until U is less than that. But Java doesn't have a repeat until. So all it has is a do while. And is it clear why we want to do while? Because you want to do it at least, what you want to execute it at least once. Okay. But the thing, one of the things that kind of comes up is, okay, well, our efficiency is 2/3. Can we do a little better in terms of that? And I like to think of this as kind of carving first with a chainsaw and then with a gouge. So generating from the distribution from the majorizing function is like the chainsaw. And then when we accept only certain numbers of them, that's like kind of chiseling it down to the exact shape that we want. And so, well, one of the things that comes to mind is what is the cause of the relative inefficiency? It's all these places in here where our rough cut is not closer in matching the density that we want. And so what's this one solution to that in this particular case is to choose a trapezoid majorizing function, which, as you can see, more closely resembles the shape of the PDF we want. In other words, we're not even generating stuff out here. We're only generating things which are going to be like this, and we now know how to generate from a trapezoid distribution. In fact, in this particular case, we can identify what these are. Okay. So our majorizing function, we can exploit the fact, remember our uniform was at 3/2, and that was the tangent there. What we want here, and then if you remember kind of when you're with your function stuff about, because this is a convex function, actually at both ends, that means that the tangent is always going to be above the function itself. And what is the tangent at 0? How would we determine that? We'd actually take the derivative and evaluate it here. So you all remember how to take the derivative, right? So the derivative here would be, it would be 6x minus, I'm sorry, 6, because the x gets killed, minus 12 x. And so at 0, if we evaluate it at 0, we see that it's actually 6. And just to check concavity, you remember we check concavity by the second derivative. And so the second derivative would be minus 12. It's negative, and so we're definitely concave. Okay. Did I say convex before? Yeah, I meant concave. Okay, so that's where you get the 6 from, and then you do a similar thing over at this end, and you get a kind of a minus 6, which is the slope there, and so that gives us the formulas for the majorizing function, and then identify. And it turns out that the points here are at 1/4 and 3/4. And so we can compute the area actually kind of using our decomposition thing. We have a triangle, a square, a triangle, a rectangle, and another triangle. So it'd be 1/2, 1/4 times 3/2, which is the height, and then 1/2 of 3/2, which is the base. And so the area turns out to be 9/8 is what this works out to. And so the efficiency is 8/9. And so by kind of more closely matching the shape of the PDF, we're a lot more efficient. Except that now we have to do a little more work to generate our test random variables. So like a first, and then the tricky part is that the ratio of the two, now we have three functional forms because our majorizing function has three functional forms. And so we need to kind of worry about that. So as the first cut, so we look at the ratio, and it turns out to be these three. So just as a check, so 6x is our in the range between 0 and 1/4. And so 6x times 1 minus x over 6x, the 6x's cancel out, and we just left with the 1 minus x. For that range, for the middle range, we've actually already done this for the uniform, so we can have that. And then for the other end, the 6, 1 minus x cancels this, and we're just left with x. And so that's the functional form of that ratio is that. And so the first cut at the method is we'll say, okay, we'll generate a uniform, but then our trial is going to be a trapezoid, 0, 1/4, 3/4, 1, as we've shown. But then the while test, it needs to, we need to have a different one for each of the three ranges. And so if y is less than 1/4 and u is bigger than this ratio, or y is between 1/4 and 3/4 and u is bigger than this ratio, or y is bigger than, oops, 3/4. Somehow the 4 got missing, and u is bigger than y, and then we return y. So that's a first cut because ideally, and if we already had an implementation of the trapezoid, we can kind of be lazy and kind of do that. But just to make sure that I encourage kind of going from the raw materials. So basically expanding all that. In other words, how do we generate from this trapezoid here? Well, let's expand all that. And so what we're going to need is we're going to need 3 random variables now. We're going to need 2 to generate using the composition method for the trapezoid, and then we're going to need the third one to test whether we accept it or reject it. And here's where you need to keep your finger on your place a little bit. It turns out that remember for the trapezoid, we had 3 probabilities. So you might be tempted to have this be less than 1/4, but it turns out that the probability here is 1/6. So we have 1/6, 1/6, and 2/3 are the way that it works out. And so you need to make sure that that's, I mean, where does that come from? That comes from the fact that we need to scale our majorizing function to be a PDF. And so, and when we do that, then these are the probabilities that come out. And if you get that wrong and you generate them and you look at the histogram, it looks all weird. So you have to get that part right. Okay, so this is where this combines all 3 of the methods that we have. So the outermost method is the acceptance rejection. So we're generating from a trapezoid and accepting or rejecting depending on that. For the trapezoid, we're using the composition method to generate from it. And for each of the pieces, we're using the inverse transform method to do each of the triangles and the rectangle. So this encompasses all 3 of those. Okay, so now let's look at another one. Yes. So if you look at it, well, here, let's work it out. So remember that or maybe I screwed it up. So that's, if I did, I'll find out here. So this is our, all right, so what do we need for, we need the height. So here we have our P0, which is 1/2 the base, which is 1/4 times the height. P1 is simply the base, which is 3/2 times the height. And the third one is, again, 1/2 the base times the height. And so we know that 1 must be equal to, well, the height multiplies all of them. We have 1/8 plus 3/2 plus 1/8. Yeah, yes, I'm sorry. Yeah, 1/2, thank you. So 1/8, so that would be 1/4. So this is H times, what this is 1/4 plus 1/2, which is 3/4. So H is H times 3/4. And that's equal to 1. So H is 4/3. So P0 is now 1/2 times 1/4 times 4/3, which is 1/6. And the rest. So that's why the scaling is important. We need to do this based upon the we need to, for the composition method, we need to actually look at the PDF itself and figure out what those probabilities are. But when we're doing the acceptance rejection, we need, bless you, we need to look at the majorizing function itself. That's why I say you have to keep your finger on your place. Yes. I usually like to say generate U. I mean, kind of mimic what I'm doing here. When I say that they're available, I say, okay, generate a U, because sometimes you have to generate more than one. Yeah. Yeah. Well, see, now if you're coding this, you'd have to say something generate or something draw, or however you do it, or next uniform. So you'd have to actually do that in the. Yeah. Yes. Yeah. Okay, so now here's what's interesting about this one is that if we now look at a beta 3 and 2, see it for this one we were concave at the origin, but for this one we're not. For this one we're actually convex at the origin, and then we're concave over here. And so how do you deal with that? So if we were to try to do something similar, the problem is that the the tangent at the origin is 0, or I mean, it's flat. It has a slope of 0. So we can't do that, but what we can do is we can actually find the tangent, which is somewhere else. And this requires a little bit more manipulation. We could have a uniform majorizing function on this as well, but I'm going to skip right over that and go right to kind of a more efficient one. So the majorizing function here is going to be, it turns out a 3x gives you exactly a tangent here. We could have chosen a steeper slope. But again, that would be, you know, the optimal, this is sort of the optimal triangle majorizing function because it's as close as possible. You know, you can't go any shallower because it won't majorize. And if you go any steeper, you're kind of wasting stuff. So this is about as good as it gets. So it's sort of, you have a line 3x up to here, and then 12. I like to write it like this because when we're working with these sort of 1 minus things, it turns out to, the expressions work out a little bit better. And if we solve for where they meet at 4/5. And so the area, okay, they meet at 4/5, but at 4/5, the height is 12/5. So this height is 12/5. Get that by plugging into our majorizing stuff here. Our base is, so the area is going to be 1/2 the base times the height, which turns out to be 6/5. And so the efficiency is 5/6, which is approximately this 0.8 something. You know, generally you want to shoot for something like 80% or bigger. Okay, so the first cut is, since we kind of know how to do triangles, we could kind of do it this way. We have to pull the same deal here. If our triangle turns out to be below, if our y turns out to be down here, then we need to look at this ratio. And if our y turns out to be in this area, we need to look at this ratio. So those are the two different functional forms. And so this is a way to combine all that into one Boolean expression. So y less than 4/5 and u bigger than this ratio, or y bigger than 4/5 and u bigger than the square. So like if you notice that this, between this and this, because these are mutually exclusive, only one of these ors is going to be valid. And then if the other is, well, if u is bigger than that, then we keep doing it. And then once u is less than that, then we return it. And really, what I would prefer would be to kind of unpack what's going on here with the with the composition method. So I'd want to do a u, a v, and a w, uniform 0, 1, and then do a composition on that. And I'll leave that for the interested or the disinterested students. So, okay, so now I mean, a lot the kind of the original the original ones on this that focuses, that kind of focused on a, you know, if I have like a PDF here, as long as it's bounded, I can always kind of try to do a uniform and that'll work. But what about the normal distribution, our bell-shaped curve? It's going to look like this. And so do you see why a uniform isn't going to work? Yeah, well, the main thing is the area under this is going to be infinite. And the key is you need to have a finite area. Otherwise, in other words, I can't scale an unbounded uniform to be a PDF because the area is infinite. So what can I do? Well, it turns out that there's actually I'll kind of there's a distribution named after Laplace, even though Laplace evidently came up with the the Gaussian distribution before Gauss. But they named it Gauss. Well, Gauss was just sort of a big deal or something. So I guess they kind of gave him a consolation prize and gave him the double exponential distribution, as the Laplace. So the Laplace is actually it's a double exponential distribution. So it's we've seen the single exponential, right? That looks like this. The double exponential is just you kind of rotate the thing around, and so it's kind of symmetric. So it roughly looks like the shape of a normal, and because it's it's kind of basically its functional form is e to the minus absolute value of x, and I think I multiply the whole thing by half. So that's the that's its PDF. That's so that gives you one of these, the PDF of a symmetric one. You can shift it to and stuff like that. But it turns out, and here you have to be kind of watch out, because this decays as linear in x, whereas the normal distribution, remember the normal PDF is this this beast. This decays as x minus x squared. And so what that means is that, bless you, at least past a certain point, asymptotically, the Laplace is always going to be above the normal. Why? Because the normal decays as e to the minus x squared, 2 in this case, but whereas the Laplace decays as e to the minus x. So I mean, the 2 doesn't really matter asymptotically. It's the x squared that matters asymptotically, because it's negative. It decays more rapidly than this once you get above it. So in other words, this is a legitimate Majorizing function, and because it is because of its functional form, it is in fact have a finite area. So even though both the normal distribution and the Laplace distribution have infinite tails, it still has a finite area, which infinity is really weird. I don't know if you've noticed. And it's not, it isn't clear if I have a function that has an infinite tail, some have finite area and some have infinite area. All depends on how rapidly they decay. There's a truly bizarre distribution called the Cauchy distribution, which looks like a normal with a slightly heavier tail. Turns out to have a finite area, but it has undefined mean and an infinite variance. And it turns out to have some very weird properties. And things like that arise in chaos theory and stuff like that. Get into that. All right, but okay, so here's our normal PDF. When you did probability, did they get to that level? And did they show you these formulas, or is this new? They did. They gave you the field method of probability. Okay, well I mean, okay, now you've seen this is the normal PDF. That's the functional form, the standard normal. And then I won't go into the math, but it turns out that in order to you can figure out what this is, and the key is that tangent point right there. You figure out exactly where that tangent point is, and then you can prove that at that point, the Laplace major, this function, which is only proportional to the Laplace distribution, it actually does majorize it there because of the way the functional forms work. And so it turns out the majorizing function for that is this guy right here. And so, and then miraculously, when we look at the ratio of the two, then we actually get a, kind of an interesting expression, which is actually fairly, not too bad. So either minus absolute x minus 1, the whole thing squared all over 2. So that's the, that's kind of the ratio. And the key here is that we can generate from a Laplace. We've already figured out how to generate from an exponential, right? We've done that before. It's minus the log of u, right? And so the negative one is just going to be the other side. On this side, it would just be the log of u, and that's going to be a negative value. And we want to choose, we can generate from Laplace using a composition where with probability of half, we go this way, and a probability of half, we go the other way. So basically, we flip a coin. If it comes up heads, we choose the positive side. If it comes up negative, we choose the negative. It comes up tails, we choose the negative side. So we can use that to generate our sort of trial random variables. So kind of taking a first cut, basically it's the Laplace with a parameter of 1. We have a uniform Laplace 1, and then our test, our ratio test is all this, and then yeah, okay. So we want to expand it to this. So again, we typically, if we're using the composition method to create our trial random variables, we need 2 random variables for that. We need a third one for the acceptance rejection. So we have u, v, and w. And say sort of v is less than a half, then our test is going to be minus the log. Here. Yeah, okay, so minus the log, that's positive side, otherwise come up tails, and so we just have a regular log, which is going to be negative, and then we do it on our test here, like that. So okay, so now in the class code of, I've implemented that. I'm not going to do it in front of you just to save time, but but here's how you here's a way of doing all that. So I'm extending random variate base. I'm calling it normal AR variate just because there's already a normal in SimKit, but I want to use this one. So here's my UV and W just to kind of match what are there.
Stir, your code isn't showing.
I have to end slideshow. Okay, so this is the Java one. It's in the Python one as well. If I have time, I'll show you that. Okay, so here U, V, and W, the Y is going to be what we do. So I'm just defining those. So I draw from U, V, and W. If V is less than a half, then I'm going to set Y to minus log of W. And then now here's sort of the weird thing is that we all learn log as ln to distinguish it from log base 10. So ln is the natural log, and log was sort of the log base 10, but it turns out that, well, for mathematicians, log base 10 is just nonsense. Nobody in their right mind uses it. Everybody uses the natural log. That's why it's called the natural. And so I think the people who wrote programming languages were also from mathematics. And so the natural log in programming is all log, L-O-G, not ln. So it's so when we want to translate ln into code, it's always log. Why? I have no idea. Anyway, but that's what there is no ln in any language that I know that. Okay, so these are the exponentials, and so here's the test. So our u, and so here's e, that's the exponential minus, now I divide by, instead of dividing by 2, I multiply by half. Java doesn't have the exponentiation operator. It would be nice if they did. That's one of the things I think they left out that they should have. But anyway, what they do with the absolute value of y minus 1 squared, we use the POW function, and then we return y. So it has no parameters because it's just standard normal. If we were writing this for real, we would want to add the mean and the standard deviation, or the mean and the variance, and then have and then instead of just returning this, we would return the mean plus the standard deviation times this, but we're not doing that. And so, see, I kind of copied and pasted here. So I'm gonna refactor, oops, I'm gonna refactor this, rename it normal. Okay. So let's generate how many I got. I'm generating 1 million of these, and I'm printing them out to a file just to see whether I did it right. And this is to make sure that I'm actually getting the one that I created, not the one in SimKit. So it turns out, see, when you add a search package like this, what the random variable factory does is it looks in the user defined search package first. The reason for that is that if for whatever reason, if you have a better way of implementing any one of the distributions that are built in, or if then this will always override that. So you can always, if you say, bus doesn't always doing, I have a better way of doing this, you can always just override it, and that automatically happens. All right, so let's see how that did. Okay, how do we do that? We just sort of suck in the data. And okay, now where this was in my, I think I put this in NetBeans projects. Oh, 2, it's code. Wait, I got it right? No, can't. Oops. Class COD. What are the problem, I mean, I see what I did. There's no such file, but I mean, it's right there. Ah, okay. Yeah. Now we can sort of check that. That looks pretty much like a bell-shaped curve to me. Once you can find the freaking data. And, okay, so for those of you in Python, it's in the random pi one. And it's basically the same deal, except that because it doesn't have a do while or even a repeat until, pulling this thing of having an infinite loop while it's all true, generating our guys. And then the same test, if u is less than a half, we choose minus log. Otherwise, it's a plus log, same test. And then, but now it's kind of the reverse. If it's less than that, then we break and we return the y. And if we run this,
Hey, sir, I'm not seeing any of the code.
you can't see it, can you? Okay, I do have 2 minutes here, but okay, where are we? All right. Okay, so all we need is the generate method. U, V, and W are uniforms. If we test if V is less than a half, we have minus the log. Otherwise, we have the plus log. And then now our test is the opposite of that. So if it's less than or equal to our test ratio, we break. So that's how you kind of do a do while in Python. And then since I'm having a hard time finding these things, I'm going to put this in my home directory just to make it easy. And let's, how many I'm generating? Let's do 1 million of these as well. And then if we now go and read that in, and now do a histogram, we basically get a As you saw, it was a slightly different one because the data are just a little, randomly generated, but it still looks pretty. Oops. Yeah, so here was a reading in. Oops, yeah, here I was reading in the Python generated one and then doing the histogram. And it looks roughly the right thing. So what that shows is, I mean, basically, as weird as this is, it actually works. So, okay, so that's it